All right, today we're going to follow a single text message on its invisible high-speed trip from the moment you hit send to the second it arrives. We're breaking down the incredible journey of a wireless signal.
I mean, have you ever really stopped to think about it? You tap, send, and in the blink of an eye, your message is there. It feels like magic, doesn't it? But it's actually a high-speed, high-stakes journey through a complex and totally invisible world. So how does it really work? Think of it like this. We're going to follow our message from the moment it's born, watch it fly through the airwaves, dodge all sorts of obstacles, and see it through until it safely reaches its destination. Our journey starts with crafting the message itself.
Okay, so our journey begins right here, inside your device. Before our message can even think about going anywhere, it has to be prepared. It needs to be translated from digital bits, all those ones and zeros, into a physical signal that can actually travel through the air. First things first, our signal needs a road to travel on. That's its frequency. Just imagine the entire wireless spectrum is this massive, sprawling highway. Frequency is the specific lane assignment our signal gets, and that's what makes sure it doesn't collide with, say, a radio broadcast or your neighbor's Wi-Fi.
Next up, how loud does our signal need to be? Well, that's its amplitude. It's basically the power or the strength of the signal. A higher amplitude is like shouting across a noisy room instead of whispering. It just makes the message that much more likely to be heard clearly on the other side.
And this part is kind of like magic. Modulation is the process that packages your text message, all those ones and zeros, onto the physical wave we just talked about. It does this by carefully changing the wave's frequency or its amplitude. This is literally how we embed our information into a signal that's ready for its big journey.
So, our message is all packed up and ready to go. Now, it enters the wireless highway, the air itself. But, not all highways are created equal, and the size of our road makes a huge difference.
The size of our lane is all about bandwidth. As you can see right here, a narrow bandwidth is like a tiny country road. You can only send a little bit of data at a time. A wide bandwidth, though, that's a multi-lane superhighway, and that's what lets you stream 4K video. It's simple. More bandwidth means a higher data rate.
Okay, so how do we manage all this traffic? We all have to share this wireless highway, and there are a few really clever techniques. With FDMA, or Frequency Division Multiple Access, everyone gets their own dedicated lane. With TDMA, Time Division Multiple Access, everyone takes turns on the same lane, just really fast. And CDMA, Code Division Multiple Access, is even slicker. It's like everyone talking at once in the same lane, but in different languages, so the receiver can just pick out the one it understands.
Our signal is now speeding down the highway, but the journey is far from easy. The wireless world is a chaotic place, and it's filled with obstacles that want to corrupt or weaken our message.
Our signal faces three main enemies out there. First is noise, which is like static or just bad weather on the highway, making it hard to hear. Then there's fading. That's just the signal naturally getting weaker the farther it travels, like a voice fading into the distance. And finally, multipath. This is like an echo in a canyon, where the signal bounces off buildings and walls, and multiple copies arrive at the receiver at different times, which, as you can imagine, causes a lot of confusion.
So to fight these challenges, especially all that noise, we need one thing above all else: a high signal-to-noise ratio, or SNR. This is the absolutely crucial measurement of how much stronger our signal is compared to all that background noise.
And this chart shows it perfectly. On the left, with a high SNR, you can see our signal is the tall bar just towering over the small noise bar next to it. The message is crystal clear. But on the right, with a low SNR, the noise is almost as loud as our signal, and the message just gets lost. So the goal is always a higher SNR.
So how do we combat all those obstacles and make sure we get a high SNR? Well, modern wireless systems have given our signal some incredible superpowers to help it complete its perilous journey.
A key superpower is MIMO, which stands for Multiple Input, Multiple Output. Instead of just one antenna, it uses several to send multiple copies of the signal. These copies take slightly different paths. Remember those multipath echoes? Well, MIMO cleverly combines them at the receiver to build a single, much stronger and more reliable signal. This was a complete game changer that made modern Wi-Fi and 4G possible.
And there are other powerful tools. Beamforming acts like a smart spotlight, focusing the signal's energy directly at your device instead of wasting it by broadcasting in all directions. Then there's OFDM. It cleverly takes our big highway lane and splits it into thousands of tiny, slower sublanes, making the signal much more resilient to interference. And finally, all of this is handled by the physical hardware known as the RF front end, the actual antennas and amplifiers that do the heavy lifting of sending and receiving.
Our signal, armed with its superpowers, has survived the journey. It's reached the receiver. But how do we know if the mission was a success? Well, we have to measure the performance.
We judge the success of the journey on 3 key metrics. Throughput is the actual speed we achieved, how much data got through per second. Latency is the delay, how long the journey took. And the bit error rate tells us about accuracy, basically how many of those digital ones and zeros got flipped by noise along the way.
So where does the signal finally arrive? It's received by the Radio Access Network, or RAN. This is the part of the network you actually see, like the cell tower, which is called a GNB in 5G. From the RAN, the core network takes over. You can think of it as the brains of the operation, managing everything and routing your message to its final destination. So let's just zoom out for a second. This slide sums up the entire journey we just followed. It starts with creating the signal in what's called the baseband. It's transmitted by the hardware, it has to navigate all the challenges of the wireless channel, and it's finally received and processed. All those terms we discussed are deeply interconnected parts of this one elegant system.
And why does this all matter? Because understanding this journey isn't just an academic exercise. These concepts are the fundamental building blocks of all wireless technology. Knowing them is essential for designing new systems, for acing a technical interview, and for just understanding the connected world all around us.
Which brings us to a final thought. We've seen the journey our signal takes today. As we look towards the future of 6G, which of these fundamental ideas, MIMO, bandwidth, beamforming, do you think will need the most radical reinvention to get us there? Thanks for tuning in.